Kano.
Yes, Kano.
ഇതില് ചില ഇൻസ്റ്റലേഷൻ പ്രോബ്ലംസ് ഉണ്ടെന്ന് ആരോ പറഞ്ഞു രാജേഷ്. അത് എനിക്കും തോന്നിയായിരുന്നു.
രാജേഷ് പറയുന്നുണ്ടായിരുന്നു. രാജേഷിനെ ഇതുവരെ കണ്ടില്ല പക്ഷെ.
അത് എനിക്കും ആദ്യം ചെറിയ പ്രശ്നം ഉണ്ടായിരുന്നു. പക്ഷെ ഞാൻ അത് കഴിഞ്ഞിട്ട് കുറച്ച് അങ്ങനെ ഇങ്ങനെയൊക്കെ ട്രൈ ചെയ്തപ്പോൾ അത് ശരിയായി. അതൊരു പെർമനന്റ് പ്രോബ്ലം ആണെന്ന് എനിക്ക് തോന്നിയില്ല. അതുകൊണ്ടാണ് പിന്നെ ഞാൻ മാറ്റാൻ.
ഇതൊരു പുതിയ പാക്കേജ് ആണ്.
ഇത് MIT-യിലെ ഒരു പ്രോജക്റ്റ് ആണ്. അതായത് ടീച്ചിങ്ങിന് മാത്രം മൊസൈക്ക് എന്ന് പറഞ്ഞ വേറെ ഒരു സാധനമുണ്ട്. അതില്
അത് കേട്ടിട്ടുണ്ട്.
അതിന്റെ ഒരു ഭാഗമാണെന്ന് തോന്നുന്നു. Okay.
I think we can start.
Okay. So we'll start today's session. We'll continue with the discussion of statistical modeling techniques and how to compare models, evaluate models. This time I am also introducing one or two packages which are very useful. One is called statistical modeling, which is actually, I think, is under development, but I think there is a version on the CRAN also, which I was able to install. That is why I thought I'll use that. But some people have said that they have difficulty in installing it. Any suggestion on the installing? If you can do it outside our studio, I mean outside the script in the console, and then come back and use the library command, it may work better. പിന്നെ ഇതിന്റെ ഡെവലപ്മെന്റ് സ്റ്റേജിലുള്ള ലേറ്റസ്റ്റ് വേർഷൻ ഗിറ്റ്ഹബിൽ ഉണ്ടെന്ന് തോന്നുന്നു. അപ്പൊ അതും ട്രൈ ചെയ്യാം. അഥവാ ഇൻസ്റ്റാൾ ചെയ്യാൻ പറ്റിയിട്ടില്ലെങ്കിൽ ജസ്റ്റ് ഫോളോ അലോങ് ആൻഡ് ദെൻ ട്രൈ ലേറ്റർ. സോ ഓൾസോ നീഡ് tidyverse and these two commands, these two packages are trying to, okay. So once we have the packages in the system, we will again use the old data because that is familiar to us. So this is cars 93, which is data on 93 cars. And it includes several variables, various types of variables also. So we have already made a couple of, or more, maybe 3 models. First one, in each of these models, we are trying to predict mileage by MPG city. That is the variable which is dependent based on the other variables. We have used 2 or 3 choices. One is just simply based on the horsepower, which is model 1. Then we are using origin plus horsepower. Origin is a categorical variable which codes for US and non-US cars. So whether that has an effect on the mileage. So that is what it says. And then you have origin, horsepower, and the interaction between origin and horsepower. Now we have talked about interaction. Interaction means that the 2 independent variables influence each other. So how does that affect the model? So if we put in an interaction term and test for the significance, if it is significant, we are supposed to keep the interaction term. If it is not significant, we throw out the interaction term. So that is the classical teaching. So we are creating 3 models, and each of these models we are looking at the sigma. Sigma, as you know, is the standard error of the regression. That is the standard error of the standard deviation of the dependent variable, which is left after explaining the model. That is, the model explains part of the variation. So what is left behind after building the model is called the standard error of the regression, or it is also known as a root mean square error value, or sometimes just as a sigma. So we can look at the various models, and the idea of creating the model is to reduce the sigma. So the one model which has the lowest sigma value is supposed to be the best model. So in this one, as you can see, we have three models, and the model with the two variables plus the interaction has the lowest sigma value. That is 4.18, 4.02, and 3.9. It's not very different from each other, but still there is a slight reduction in the sigma. So we can generally say that the last model with two independent variables plus the interaction between them is the best model. Of course, these are not the only models possible. We are just giving an example. We can test various other combinations, but model building base is based basically on our knowledge of the domain. We should know what will influence mileage. Then only we can put in. Of course, another approach is to have an automatic algorithm by throwing in everything and then trying to take out one by one. If you know nothing about the basic relationships, we can try that. So this time we are using statistical modeling package. It has some special functions. First of all, it has a function called F model, which will actually just graph your model. So you don't have to, we have seen last time how you can use ggplot to plot, which is very good, but this is based on ggplot. The same plot can be produced with just a few lines of code. So that is the advantage of using the statistical modeling package. So we'll see that. So we have these two graphs. One is the parallel slopes model, which says there is no interaction term. So USA is the orange line and the green line is the non-US. So you can see the non-US cars have generally higher mileage compared to the US cars. And here we are assuming, or we are forcing a model with no interaction. So these slopes we say are parallel to each other, so they will not interact. Whereas the second one, where we have put an interaction term, uses a interaction model where the slopes, the lines will be crossing each other. So which means that at each level of one variable, the other variable will vary. So it is not parallel. So these are the two. So F model is a very simple function which will help us to plot the model and see how it is. But here what you see is that there is a the order in which you specify these terms, independent variables, is important, because if you go one thing further, we can try adding a third variable, which is man trans available, which means manual transmission available or not. So that's another categorical variable. So we are going to build a model 3. So we have model 3, and then we are looking at the summary of model 3, which actually also has a sigma around 3.96. So if we graph this, that is just F model, horsepower plus origin plus and trans available, then we'll see what happens. So then what happens is it produces two graphs for each level of man trans available, no, man trans available, yes. And in each one, it plots the dependent variable against two other variables, that is horsepower and the origin. So we have 1, 2, 3 independent variables and one. So this is how we can. So here, how you specify this model is very important. The first term after the tilde should be the X variable, that is the X-axis variable, which is horsepower in this case. The second should be the color variable, that is the coding by color. That is, the line will be coded according to origin. So that is the second term should be the origin, the color variable or coding by color. And the third variable will be the faceting variable. So these are the facets, as they say in R, in ggplot. So there are two facets. One is man trans avail no, man trans avail yes. So if we can actually play around with this, if you change origin to the last one, then you will have the faceting variable as the origin, and the other thing will be the manual transmission variable or not. So you can actually try that if you want, or maybe I can just show you. I copy the slip, this script, and try to change that. So this origin will be put the last. So as you can see, it is just a reverse. So it it takes the origin as the faceting variable and the man trans avail as the grouping variable. So it's a very simple script which gives us the facility to look at the data and the model in various ways. That's all. I mean, these are not final graphs or anything. These are all exploratory commands. So the syntax is like this: f model. The first, then you just put the tilde. There is the x variable. Now the model itself gives the specification, so you don't have to actually put the dependent variable here in this command. You just put the three independent variables in that particular order. So the first one is the x variable, that is what is represented on the x-axis. The second one is the grouping variable, or what is represented by the color. The third one is the faceting variable, which is represented by the two facets. So this is an important function, f model. Similarly, in the statistical modeling package, there are other commands. One is called effect size, effect underscore size. So we put effect size. So it gives us what is the change. Now we are asking for the effect size of origin. So origin is in US to non-US. So what happens when what is the difference between US and non-US? That is what it actually effectively says. So this is, and you are holding these two things constant. Horsepower is held at 140, and manual transmission available is held at yes. This particular situation, what is the difference between US and non-US is what is given here. So you can use other models also for the same thing. But here, this one is an interaction term, the model with an interaction term. So actually, this may vary with different levels of horsepower. You can try that. So this is how you do that. So you can actually, for the continuous variable, it will give you the slope. That is, suppose you want to know the effect size of horsepower, it will give you 0.06. That is the slope minus, and it is horsepower is held at 140, and this is USA, and manual transmission available is yes. So when you go from horsepower 140 to this, in this range, what is the, well, of course it will be the same throughout. Then you can actually change the specifications. You can say you want to see what is manual transmission available, no, then you get then these. When here, of course, it's not much different. You can also look at non-US. So of course, slope is very similar because we have forced the slope to be similar. So this is effect size, the command effect size. And there is another command called evaluate model. Evaluate model is just like your tidy command, the broom command, which we have learned earlier. When it produces a database or data frame out of the output of your model. So when you say evaluate model, what you get is this, that is for each level of these in the whatever is in the model, you have three independent variables in model 3, that is horsepower, manual transmission, and origin. So for each combination of these three, what is the output or what is the predicted mileage? So that is what is given. So that is evaluate model. And you can also specify evaluate model at each whatever level you are interested in. So if you just specify the terms, you will get specifically model output for this. So this is one general familiarity with the statistical modeling package. So any questions so far? I mean, most of these things we already learned. It's only just doing it by another package. That's all. Okay, now we go to another important aspect, which is prediction validation. That is, see, we have seen that how is a model validated or evaluated is by looking at 2 or 3 statistics. One is commonly looked at as one is the R-squared value, the adjusted R-squared, which is the proportion of variability which is explained by the model, and this can vary from 0 to 1, and because if the 1 means totally explained, which is not what we want, because when you have total explanation, that means you don't, that model is fits the data perfectly so that it cannot be used for any other data. So that is not what we want. So prediction, we have seen that by looking at the square root of the mean residual error, we can, that is the second point, that we can assess how well a model fits the data by looking at the RMSE value or the sigma value. So all models aim to reduce the RMSE so that a better model is one with a smaller RMSE value. However, since we are testing the fit on the same data, so there is a problem here. We are using data set and getting a RMSE value on the same data. So there is a problem of overfitting. That is, it will perfectly fit the data, I mean, it will very nicely fit the data that we are using because the model is built on the data. But we don't know. What we want to know is how the model will perform in the new data. That is, how will it predict new set of independent variables. So that is what we want to know. So if you want to know this, one common approach is to have 2 data sets. We can split the original data into one half called the training set and the testing set. So we develop the model on the training set and then we predict on the testing set. So then we will know how well the model performs. So there are many approaches to this, to do this, and that we will look at one by one. One first and the easiest is called the validation set approach. That is simply, as I said, we divide the data randomly into 2 sets, the training set and the test set. The model is created using the training set and the predictions are made on the test set. So then we can calculate the RMSE on the test set and see how well it performs. So the model created using the training set is assessed using the test set. Because, and that is what the technical term for this is, that the test set is naive, or it has not been exposed to the training data. So it will correctly provide you with the parameters. So this avoids the problem of overfitting. So this is one way. It's very easy also. So the first step is splitting into the training and testing data. So we can use various levels of splitting. We can use 50-50. We can use 75-25. Here I have used 60-40. So cars training set. First of all, you create a variable in the additional variable in the data called training set, which is actually our binom. We know this command. It is a binomial. It will create ones and zeros. So we have the n number is n row cos 93. So how many rows cos 93 has? It will create so many ones and zeros. And the probability above, and we have put the probability as 0.6. As we know, when you flip a coin, you give the probability also. The default is 0.5, but if you want to change it, we can change it like this. So we are using 0.6. So we will get around 60% of ones and 40% of zeros in this called the training set, cars 93 training set. So this command helps us to do that. And then you can look at this particular something wrong happened. Let me see. me see if this worked. We can try out the command here. Put the yeah, we are getting the ones and zeros, so it should be okay. But I don't know what went wrong. Or maybe I can put zero length variable name. I can use tidyverse to do this. Let's see if this works. Yeah, now we have a column of training set. Okay, so we will call this as COS93. So we are saving the same name. For some reason, the other command should work, but I don't know what happened. Anyway, so we have created a new variable for the COS93. So we will look at this. So this one last variable has a training set true, false, like that. There will be about 60% true and rest should be false. So true and false, as you know, are coded as 1 and 0. So we divide the training, this data into two data sets called training and testing. First one will contain all the rows where the training set is equal to 1 or equal to true. And the rest, the other one will be 1 equal to 0. And then we can also look at the instead of structure, we will just put head. look at these two data sets, training and testing. So if you look at this, you will find that in the training, you have the last one, everything will be true, whereas in the second one, everything will be false. And we can also look at so there are 61 rows in training and 32 rows in testing. So that is about 60-40. So now we will use the training set to create our models. We are creating two models. One is first model where there are only two independent variables, that is origin and horsepower. And the second one where there is these two plus the interaction term. So that is these two are the two models we are creating. So we will call them model underscore 2 underscore training and model underscore 2 underscore 1 underscore training. So we are creating those models. So that is a second step. So then what we can do is use these models to predict the testing data. And then we save that predictions as prediction underscore 2 and prediction underscore 2 underscore 1. So these are corresponding to the two models we created. And we can look at how those predictions look. So it will have all the variables. So the last one will be, last variable which is added will be what known as, is always named as model output, model underscore output, which is the predicted value. Just like in the other Broom package and all, we saw it is called fitted. Here it is called, it's the same thing, but it is called as model output. So we can look at these two model outputs. And then then step 4 next is calculate the mean square error, which is of both models. Mean square error is the mean of the squared differences, that is predicted minus actual. So the predicted is what is known as model output, and the actual is what is the same for the same row or same object or same observation. What is actual mileage? That is predicted minus actual. These are the differences. So you take those differences and square them, and then you take the mean of the squares, that is sum them and take the average, and then you take the square root of those the mean value, which will give you the RMSE, the root mean square error. So for these two models, the first model it is, and second model. So as you can see, these RMSE values are considerably higher than what we got from the whole data set. So this is because we have trained in one part of the data set and used that model for testing in the other part. So the data which we have used for testing is not the data on which we have trained the model or we have developed a model. So that is why we don't get so there is no overfitting. So this is more realistic estimate of the RMSE than the what we have originally formed. So we are avoiding this pitfall of overfitting. So this is very important. So and then now we can actually compare with the two sigmas also. So then you will find that these are much smaller. So whereas these two are much higher than what we have. is 4.95 and 4.77, whereas it is here it is 4.02 and 3.9. So the second one definitely has a lower sigma compared to the first model, but actually the estimated RMSE from the testing data is much higher than what we get for the overall data. So that this gives us a better understanding, better estimate of our error. Now, the same principle can be extended further. Instead of just dividing the data into a test and a training set, and looking at the model in the training and then using that to predict the testing, we can actually do what is known as k-fold cross-validation. K-fold cross-validation is an extension of what we have just seen. It again involves several steps. One is the data is split randomly into k sets. K may be 5, maybe 10, maybe 4, maybe 6, whatever you can decide. So if you take k, the 1 by k will be set aside as the testing, and k minus the 1 minus k sets will be used as the training. That is, if there are 10, the data is set into 10 equal parts, one part will be the testing and the 9 parts will use the training. So one of these sets is set aside as a test set. The model is developed, trained using the rest of the data. Now this is done randomly. Now this is repeated again with another set of k subsets. So if you choose k equals 10, it will be again split into 10, and then another subset will be taken as a testing, and this will be repeated. So whatever number of times you want to repeat, you can repeat this. That is called k-fold cross-validation, and then you get the average of all these. You estimate the average of the values of the RMSE. And sometimes you can even go further and you can use the split into k folds is repeated several times. That is, first of all, you divide the data into 10 subsets and use this k-fold cross-validation. Then you repeat the whole process again. Then you repeat it again. So you can do that several times. So that is repeated several times, and the average is used. So k is usually fixed as k equal 5 or 10. Because people have found that these are the best options, because there is no advantage to using either less than 5 or more than 10. So something between 5 or 10 can be used. And the advantage of statistical modeling is that it gives you a function which will do all this for you. You don't have to worry about how to split this randomly and all that. So this is called a CV pred error function. CV underscore pred underscore error. So we can just use the CV pred error function, and it has two, we will come to that. So we can use so suppose you have the model 2, which uses 2 predictors. So we can use what happens, we can use that as a CV pred error model 2 and then save the output as trials model 2. So first of all, we look at, we'll just run all this. So the first thing output is what you see here is the first command, that is summary of sigma which we have calculated on the original data, which is 4.02. Now this is trials model 2, and then we have used the trials model 2 sigma, and the square root of this is given as the 4.09, and then same thing happens with 2.1. This is 2 and this is 2.1. So this is 4.02 goes up to 4.09, and here 3.9 goes up to 4.04. So when we do the averaging of repeated split and random split and calculation, we find that it is not as bad as we expected. It is a little bit more than, but still it is higher than what we originally calculated. So this is so this is what the trials model 2 will look like. That is, it will have two variables. One is called the mean square error, and the model is what is the model used, that also will be specified. So for 2.21, it will be the same thing, that is MSC and model. So we are taking the square root of this MSC. That is what square root of the mean of the MSCs. So that is what we are doing. So when we get the mean, we can actually compare it with a t-test. That is, we can use the sigma. That is, sigma from this model, as we have seen, is 4.02. And we can use this t-test. We have looked at the one sample t-test. One sample t-test means we have a variable, which is this trials model to $MSC, which means this is a variable which we have seen here, that is this MSC, from this data frame, which is called the trials. So we are taking this square root of this as one variable. So that will be the one variable, will be square root of this, comparing its mean with the mu. Mu is the original sigma that we have already have. Mu is model 2 sigma, and the data is data trial model 2. So if you use this command, we get the one sample t-test comparing the estimated cross-validated estimate of the RMSC with the original sigma. So we can look at the output. So it is the p-value significant. So actually the 95% confidence interval 4.04 to 4.13, and the mean of X is 4.09. So it is different from 4.02, which is the original value. So similarly for the other model also, here also we find that it is significant. That is, so what does this mean? This means that both these tests tell us that the estimated the RMSC from the test data, cross-validated and estimated data from the test data, is a little bit higher than what we originally estimated in the data as sigma. So this means that there was overfitting in the original data. So we have done the right thing to do this. So we know that these are a little different, a little higher than the original data. So the function CV predator has the following arguments. One is a k. K is the number of data. The default is 10. So here all we have used 10 because that is the default. If you want to change that, you can specify k equals 5 or k equals 8 or whatever it is. So that is the number of subunits into which the data will be divided, and one will be used as the test and the other 9 will be used as the training, and this will be repeated for all the 10 groups, so 10 subsets. So that is, but then there is another variable argument also called n trials. N trials is the same thing whether you want to repeat the trials, that is you can use it again and again. So n trials also, again the default is 5. Again you can change whatever to whatever number you want to. So if you want to do comparison of these models, we can simply use a t-test on them. That is, you can use the trials both. That is, you use this command CV predator model 2, model 2 to 1. So that these both of these will be done at the same time. Let us see how that goes. So it will have two variables, two columns. One is the MSC, the other will be specifying the model 2, model 2.1. So we have this kind of a data set. So we can use a t-test on the square root of the MSC, and we can use the model as the variable name model as the grouping variable, just using the tilde here. So if you do the t-test, what it says is whether these two are the same or not. So that is the RMSC calculated from both models. So we have we see that it is not significant. So we have a situation here where you have two models. Both of them have actually given a significant difference from the original estimate of the RMSE, which means that both of them are saying that the original RMSE calculation was did suffer from overfitting, but so we have improved by using the models. But between them, there is no difference. When there is no difference between two models, the ideal advice is that you use the model with the less number of terms. So that is, these two are not different. When you have two models which are not different, the standard rule is that you use the lesser number of model with the lesser number of independent variables. So this is known as the Occam's rule razor. This is a rule of logic. Some of you might have heard about this term, Occam's razor. It was first described by a bishop in Britain in the 12th century called William of Ockham. He said simply that when you have two explanations to a situation, you should prefer the simpler explanation. That is more likely to be correct. I mean, it's just a rule. So similar. So according to that, when you have a 3 variable model and a 2 variable model and they are not different, that is what we have seen by this t-test. They are not different. So when they are not different, you prefer the 2 variable model. So we can actually use the parallel slopes model. That is what it tells us. So this is the multiple or k-fold cross-validation technique. It's a little complicated, but I think I have explained it. Any questions on this? Okay, then let us, there is another technique which we will not discuss, not because it's the only thing, there's no point in, there are a lot of variations on this theme, but the third approach is called leave one out cross-validation. Leave one out cross-validation means if there are 100, units in the sample, suppose, I mean, in this, we have 93 cars. So you take one, leave one out and take the, develop the model on the 92 and then calculate the, sigma from the model involving the 92 and compare it with the actual value of the 93rd car. So you have the mileage of the 93rd car which has been left out. Compare that with the RMSE which is being developed from the 92 cars. So you do that for the 93 cars. So you develop 93 models and compare with one with the rest. So that is called leave one out cross. And you take the average of all this, just like we have seen. That's called leave one out cross validation. And there are packages which can do this. I won't go into the details of that. So I'm just leaving the that particular technique aside. And last, what we will discuss is what is known as bootstrapping. Bootstrapping is another approach to get over the overfitting problem. And we will use the CARET package in R to do this, which I hope you have installed. CARET is a very useful package, and currently it is one of the most extensively used ones in machine learning approaches in R. It has many functions. In fact, most of the things we have already seen can be done in CARET with a very little programming steps. So that way, CARET is a very useful package. So we will use CARET library. This command set seed 247. What it means is, if you use a set seed number, whatever number, you can use some number here. So what it does is when we repeat the whole script, if we want to get the same result, because it's bootstrapping, sometimes you get different results. So if we want to get reproduce your results, then you can use one number as a set seed, and then it will follow the same steps, and we'll get the same kind of. So first step in bootstrapping is create an object called train control. Train control using the train control command. Method should be used as boot and number 100, which means 100 times it will sample Just like we have seen earlier in the infer package. What is bootstrapping? Bootstrapping means, suppose that there are 93 cars, so it will sample one by one 100 times. Each time a car will be taken, added to the sample, and it will put back. So the sampling with replacement. So then we have a sample of 100 cars. Of course, some of it will be repetition, but so that is the first step. Then you can create the model using the train command. Train, and you specify the model here. Horsepower plus origin data cars 93. Method is LM. Then you use this specification to the argument. Train TR control equals train control. This train control is object we have created already. So that is given as specification for the TR control argument. So then that is how you create the model in the CODD package. And I've done the same thing with the second kind of model also. The second model which we have looked at, that is two independent variables and the interaction. Then after creating these two models, it is simply just a question of printing out this model. It will give you, this is output. Says 93 samples, 2 predictors, no pre-processing. Pre-processing, as CODD also has the functions to look at the variables and input your missing values. I think Dennis demonstrated this earlier, how to pre-process and all that. So here we are not using any pre-processing because our data is like a teaching data. So there are no missing values. It is a perfect data. So there are bootstrapped resampling, 100 repetitions, summary of sample size 93, 93. All those are correct. Then it gives the RMSE directly, that is 4.28, and you also get the R squared, and then you get what is known as MAE, which is also an important output from this regression, especially from the repeated cross-validation techniques. This MAE comes in a lot. MAE means mean absolute error, which is just like the difference between the predicted and the actual. But you just take the thing and remove the sign, so that makes it an absolute value, and then you average it. So that is called mean absolute error. So that's also some similar to RMSE, but another way of looking at the error. So these three statistics will be given by your CODD package using this command. And then it also says tuning parameter intercept was held constant at a value of true. So this is something technical. I mean, so CODD gives you the average RMSE from 100 bootstrap models from the original. So you can look at the other model also. So here you have higher R squared point, and RMSE is like okay, we'll look at it both at the same time. Yeah, here it is 4.28, it has become 4.08. 4.49 R squared has become 4.52, and mean absolute error also has come down. So here it says that absolutely that the model with the interaction term is performing better by bootstrapping. So these are all different approaches to validating your regression, of training a model and then using it to prediction in a testing data set, which is different from the original training data set. So that's a very important principle. Especially this kind of approach is used in many machine learning approaches, where you get the average of several repetitions as the error, and then based on this you pick your best model. So that is the principle. So that is what happens. I think that is all for today. So that is called bootstrapping. So we have learned about how to compare models using graphs, especially from the statistical modeling package. We have looked at the F model function, and the statistical modeling package also has certain other useful commands like effect size, evaluate model, and all that. we have looked at all those. Then we have looked at validation of prediction. First, very simple, that is we just split the data into two halves, either 50-50 or 60-40, whatever we want. And then we use one as the training and the second part as the testing data. And we just look at uh, the error in the testing data using the model which has been developed from the training data. So that is the first level of split data cross validation. Then that same thing can be extended further by splitting the data randomly again and again into several. That is, first of all, you can split it into a number of subunits using one as the testing data, and this can be repeated for every segment of those division. That is one way. Then we can also extend this even further by repeating this whole random allocation again and again. So we can have k-fold cross validation, and n trials can be 10 or 5 or whatever it is. So again and again you're doing this and looking at so you get an average value, which may be much better option than just using as one split. And finally, we also have what is known as bootstrapping, which is again resampling from the same data over and over again and looking at the how it performs when we do that. So these are the approaches to assessing regression. Of course, we have used a perfect database, or one with very little mistakes or any incongruencies. So we have had a very smooth run. But usually, when we have raw data, it will be it may need a lot of processing, as we have said. So that is another thing which you have to keep in mind. And missing values is important. I think Dennis had a whole class on missing values, how to impute that and all that. So all those things I'm leaving out. So this is just simply the principle of regression and how to assess a regression model. Any question?
Occam's razor ഒക്കെ ഉണ്ടോ? എന്താണ് ഉദ്ദേശിച്ചത്?
Okay, Occam's razor എന്ന് പറഞ്ഞാൽ ഇപ്പോൾ see, we have two models which have performed. Both of them, they are here. If you look at model 2 and model 2.1, both of them are different from the RMSE from both of them is significantly different from the original RMSE. So both of them are saying that there is a actually oversampling in the overfitting in the original data. But between these two, which will we prefer? That is the question. Of course, we should prefer the one with the smaller RMSE, which is the second model. The 2.1 model has a smaller RMSE. But we are looking at whether these two RMSEs are really different statistically or not. And then we are finding that it is not. So our p-value is 0.18, which means that even though it shows a slightly slower RMSE, it is not really significantly different from the earlier model. So between 2 and 2.1, there is no statistical significance. So when there is no statistical significance between two models in the performance, the principle is that we prefer a model with lower number of terms. Now here we have two models. One has two terms, origin and horsepower. The other has three terms, origin, horsepower, and the interaction between them. So when the output shows the evaluation shows that this RMSE from these two are not statistically significant, as we have seen here, p-value is 0.18. So which means that actually the one with the lower number of predictive variables is preferable, which is the one with the only horsepower and origin. And this is what I was just talking about Occam's razor, because it is a logical principle in logic, which has been described first by this person called Bishop Occam, who said that when you have more than one explanation to a phenomenon, of course he was speaking about some theological question, not mathematics or statistics, but when you have more than one explanation for a complex phenomenon, always prefer the simpler explanation. So here the simpler explanation is the one with only 2 variables rather than one with 3 variables. So that is why we say that it is we are using the Occam's razor. Occam's razor means that you're shaving away unnecessary things from the model. I don't know if that.
Thank you.
Okay. Anything further? Okay. Further progress, I don't know. I